much, Kenneth, and thank you everyone, and thanks Edward as well for the invitation to present. Because there's not many of us, please, we'll keep it informal and just ask me any questions as I go. And welcome to a couple who are just joining us now. So I will talk today about one of the notebooks in the Sandbox repository, which is called Forecasting Vegetation Condition. It's, as the title suggests, about forecasting the condition of vegetation, which we measure as NDVI, into the future. And the idea of the Sandbox came from my colleague here in Australia, Chad Burton, and also me. And there is some application of the notebook into the real world, but the real idea for creating the notebook and pushing it into the Sandbox repository was to demonstrate a forecasting workflow that users could apply to NDVI or indeed to any other spatial variable. So welcome to a few people who have just joined us. I've only just started in the last minute, so you haven't missed anything, and please feel free to ask any questions as we go. So from an applied perspective, before I get into the technicalities, I can see a few different applications for the forecasting of vegetation condition. It might be important for food security, like identifying potential gaps and preparing for drought. I'm also a PhD student at the Australian National University working on remote sensing in Africa, and I've just been working on a similar scenario for Madagascar and trying to understand the drought that was experienced there in 2019 and 2020. So this work has some application in that context. It could also be applied to rangeland and stock management. I can see that, managing the rangelands, it could be quite useful to forecast the vegetation greenness or condition for a few months into the future. So rangeland managers can make stocking rate decisions accordingly. Perhaps forest management as well. It could help people make better decisions about harvesting. And I'm sure amongst all of you, you can think of some other applications from your experience for vegetation forecasting. I'll give a very brief background into time series models now, and then give an overview of the forecast here in the slideshow before I'll change over to the Sandbox notebook and go through the notebook cell by cell. In this particular example in the notebook, we're using a time series model, and time series forecasting models are fitted to data that's observed at regular intervals. So that might be every day, every week, every fortnight, or every month, or even every year. In remote sensing, our time series aren't always regular. They might be irregular due to cloud cover and other constraints like that. And so to generate a regular time series, we resample to a regular interval. In this case, we're taking the mean NDVI across 1 month to form a time series. And then for the purposes of this forecasting exercise, we're masking the analysis to the cropland extent product. So we're only forecasting cropland, and it means that the phonology or the regularity of the time series is a bit more consistent, and it makes it a little bit easier to forecast. So if users were interested in applying this forecasting, they might consider masking the spatial data to a particular land cover like forest or cropland. I don't want to spend too much time on the real technicalities of the time series model. I'll just go through, I guess, what's important to understand. For the notebook, we have used a seasonal autoregressive moving average exogenous algorithm for forecasting, or SARIMAX. It's a variation on a number of different time series forecasting algorithms that stem from ARMA, or ARMA, which is autoregressive moving average. We can see that the S stands for seasonal. Autoregressive means that it runs a regression on itself. Moving average means that the forecast is built based on a moving average or a series of previous observations. And exogenous means that it can account for external variables, although we don't use that function in this case. The important part to understand about like the seasonal aspects of forecasting and time series is that we can think of a time series both in terms of trend, or in this case, integrated, which is the I, and a seasonal component. So that's called a seasonal decomposition of the time series. I've shown an example here on the right-hand side. We've got the actual time series in the top chart. Within that time series, we can decompose it into a trend, which is in the second one. There's a seasonal or a repeating component, which is the third. And then there's residual or a random component, which is the fourth box there. And so in Cerima or Sarimax, we have three inputs, P, D, and Q, which I'll show on the next slide. And they apply to the seasonal, again, which is the repeating pattern, and also the non-seasonal, which is the overall trend. So the important part of, again, I don't want to go into too much detail about the technicalities of the algorithm, but in the notebook, you'll see that the user does input P, D, and Q, and we've suggested some values. So it is worth understanding what they are doing. So P, D, and Q, P is the auto-regression order, and that's the number of immediately preceding values in the series that are used to predict the value at the time of prediction at the present time. So that's the moving average component. So let's say we've got a time series that's resampled at a monthly interval. So we're in now the month of April. If we were using a P, the value of P was 3, then the auto regression order was 3, then the value in April would be predicted based on values in January, February, and March, because it's using 3 months immediately preceding the present time. D is the difference order. So differencing is effectively taking the trend, which we saw in the previous slide, and differencing it back to a linear model or a straight line, so it can be easier to forecast. And that's the number of times that differencing is performed. So if you're familiar with polynomial and linear statistics, the difference order will depend on that. And there's a few tools we can use to help us choose, but normally 1, 2, or 3 is okay. And then Q is the moving average order. So that's the size of the moving average window. So once again, it's quite similar to P, although this one flows through the time series to help us calculate the seasonal components and also the trend components. So we again fit PD and Q lowercase and PD and Q uppercase to the non-seasonal and the seasonal components of the time series. That's probably the major technical component. So once we've chosen PD and Q, we can run a model. And the first step is cross-validation or back testing, so we can estimate or evaluate our model performance. So to do that, we split our data into a training set and a test set. And those of you who are familiar with machine learning or statistical learning will be quite familiar with cross-validation. So the training data is used to train the model or teach the model what we need it to know about the time series and the seasonality. And in this case, the orange line here shows the training data. So we often choose, 80 or 90% of the data as training data. And we split off the remainder, in this case, the most recent, I think it's 10 observations, as the test data. And then we can train our model on the orange training data, use it to forecast into the future, which is in the blue, and then compare our forecast to the test data, which we kept and we withheld from the training data. and calculate an error between the green and the blue to evaluate our model. So that helps us also if we run lots of different models, the error on that cross-validation helps us choose the best model. Once we've chosen the best model, we can then complete the final forecast. So in the final forecast, we include the test data, we include the most recent data in training the model, and then we forecast it out into the future. And I guess putting my statistician's hat on, I always like to see some kind of uncertainty shown with the forecast, because we can quantify the uncertainty with statistics. So in this case, we've got the forecast and we've got the 95% confidence interval around the forecast. So I will just stop sharing for a moment. I'll bring up the notebook, but in the meantime, please jump in with any questions or comments while I move over to the notebook and share my screen again. Okay, I think I've confused everyone, and so there's some silence there. In that case, I'll keep going with the notebook. So the notebook's available in the Sandbox for everyone who has the Sandbox account. It's easy to sign up. If not, you can also see the notebook on the GitHub repository for Digital Earth Africa notebooks. So the first introductory and background gives a very brief summary of what I've just described with Sarimax. There's a link there to, if you're really interested in the ARIMA and the time series modeling, you can follow that link and learn a bit more about that. And then, as the description says, the first step is to load Sentinel-2 for calculation of NDVI. As I said before, it helps our time series be a bit more consistent if we use the crop mask. Thanks, Kenneth, for posting that link to the notebook in the chat there as well. The third step is to iterate through different values of P, D, and Q. That's the Sarimax parameters, and then conduct a model selection based on the cross-validation that we just saw. After that, we can look at some model diagnostics. I haven't shown them yet, so we'll have a look at them soon. And then finally, as we saw in the most recent slide, we can forecast NDVI into the future and visualize the result. I think this cell will, it might run because I've just reinstalled, but for users who are logging in and haven't installed any packages recently, just be aware that there is an issue with an upgrade on the stats models package. So if you get an error when you run this first cell, just add a new cell and then you can run this command here, install stats models upgrade, or install it completely again, and you should be able to overcome that error. We will create a local Dask cluster for parallel computing in this notebook. It really just helps with calculating the NDVI, and after that, the steps don't require too much compute because we work in a one-dimensional time series. We do need to connect to the data cube, and after that, we set up all our analysis parameters. So we've got our area of interest here. The product that we're using to calculate the NDVI in this case is Sentinel-2. That gives us pretty good frequency that we can use to resample to a monthly frequency. And we've used a time window from 2017 to 2022. You could extend that, but of course, just be aware of the computational limitations. And here we define our resample frequency as 1 month. You could go fortnightly as well, but it's really up to the user. Of course, be aware that if you go any longer than 1 month, it can make the seasonal component of the time series a bit more difficult to quantify. We need to define a forecast length, and all of these parameters are described in the text above the cell. And that's the number of time steps, in this case, months, that we want to forecast into the future. A greater forecast length means greater uncertainty, although it's worth bearing in mind that we can quantify our uncertainty with confidence intervals and standard errors and things like that. And finally, just our resolution of Sentinel-2 and also Dask chunks for computing. So we can inspect the area. The cropland extent or the crop mask does quite a good job at identifying the cropland, which you can see in this particular area, and we mask it to that cropland. So of course, users can quite easily adapt it to another area, but I would suggest just being aware of the uniformity of the landscape, because again, if the landscape is homogeneous and uniform, it makes the time series a bit more consistent. We can then set up our query, which is mostly based on the parameters or the analysis parameters that we've defined above, and then use load ARD, load analysis ready data, to load in our Sentinel-2 data. The next step is to mask the region with the cropland extent map. So we're using the crop mask Eastern in this case. I'll load that in. As we saw in the image earlier, it does quite a good job of masking that area. And then we just use this command where to mask the data set, which was our Sentinel-2 data set, to where the crop mask equals 1. So that's the masking step. We can use the data cube command, calculate indices, to calculate NDVI on our data set. We use drop equals true to drop the bands that we don't need. So then we get this message that it's dropping the bands red and NIR, and it's leaving us with only NDVI. It's not a huge deal at this scale, but it can help save memory and data size if we were doing it at larger time scales or even spatial scales. We then use a window of 4 to resample the NDVI to that monthly time series that we talked about before. So that we use a mean, and that runs pretty quickly. We then reduce the time series to 1 dimension. So in this example, we're generating a forecast on a 1-dimensional time series, and that means that we have to aggregate the spatial component of NDVI. So this step does take a little while to complete. It's probably the most computational step in the analysis. So I'll leave that run, but I'm aware that I went through the last steps a little bit quickly, so I'll just pause and give any opportunity for questions or comments, and also welcome those who have joined us along the way. I can see a raised hand from Eileen. Eileen, yeah, please unmute yourself if you can, or in the chat if that's better.
Thank you very much for your presentation. Could you please clarify more about the uniformity of the landscape that we should ensure when selecting an area?
Yeah, of course. So the uniformity of the landscape. So I know in your introduction, Eileen said you said you're working on phonology. So
Yes.
I think you're quite familiar with this anyway. So we can see here that we have in this area of interest, there is clearly some cropland area. It looks like that's perhaps on a plateau or some kind of landform. And then there's more natural or native grasslands, and also some riparian vegetation in the area. So those different vegetation types will have different phonology, as you know. And when you get different signals, especially because we're aggregating spatially to 1 dimension, if we get different signals from different forms of vegetation, it can make the phonology year to year inconsistent. And that means that the seasonal component of the time series is a little bit mixed up year to year. So if we limit our forecasting to just 1 vegetation type, like cropland or forest or grassland, then it means the phonology is more consistent year to year. And so the moving average time series is able to more accurately estimate what's happening in terms of a seasonal pattern.
Thank you
Does
very
that
much.
answer your question?
Yes, it does. Thank you very much.
Thank you. If there are any other questions, please feel free to speak up or raise the hand, and I'll try and spot you. I think the mean is still running, so it does take a little while. Can depend on how the computer's going. So we can see in our corner that it's using, I'm just on the, it would probably be a little bit quicker if I logged into a larger instance, but I'm just on the base instance, I think with, probably get it wrong now, 2 CPUs and 15 gigs effectively, or 16 gigs of memory. So it's not using too much memory yet, but it's using quite a lot of compute on the cores. Okay, it should run quite soon. So I'll start just talking about the next couple of steps, and I'll run the cells when the data becomes available. So the next step, we'll have a look when it's available, is just plotting the NDVI time series, which we can visualize quite easily. And then we'll see the phonology that Eileen just asked about. And then after that, we split the data and fit a model. So as I said in the slideshow section, cross-validation is a common method for evaluating model performance, and we need to divide the data into a training set for training the model and a test, or sometimes you hear it being called a validation set. So effectively, all we need to do is say train data is the NDVI data, except for basically the last 10 observations. So we just say remove the last 10 observations and keep them as test data. And then the next line of code says the test data is the NDVI just with the last 10 observations. So it's a pretty nice, easy way of splitting them out. You could do it randomly, of course, but it makes a bit less sense when we're doing a forecasting time series. Often we want to pick ones that are next to each other in the time series. After that, we can iteratively move through a range of values for P, D, and Q. So once again, I've just described what they represent. It can be a bit confusing what they mean, although yeah, if you are interested in that aspect of the model, you can find the link to the moving average time series articles further up in the notebook. So the other one, just to note, is the length of the season. So in this case, we use 6 because it's in units of resample frequency. So in this case, our resample frequency is a month. And so let's say that, effectively there's a wet season and a dry season, or a warm season and a cool season. So we use 6 months for 2 different seasons. After that, we define a range for P, D, and Q. So the range is 0, 1, and 2. So there's 0 up to 3. And because there's 3 different values, 0, 1, and 2, means that 3 squared multiplied by 3 squared, there's 81 possible combinations. So when we, I guess, iterate through, we'll see that there's 81 different models that we test, and it actually runs quite quickly because the data set isn't too small. It is quite small, sorry. Once we've got those 82 models, I'll just pause again but we can generate a result table in which we show all the different, I guess, the different models and the number of iterations. I can see that our CPU is still running, so it looks like we're still calculating the mean NDVI. Welcome to those who have joined us along the way. So we're just discussing the forecasting of vegetation condition notebook, and we're up to the point where we calculate the mean across space, and the cell is just taking a little while to run. So I'll continue going through a few of the different steps in the meantime. So after we've got our 81 different models, which we've iterated through with different values of P, D, and Q, we then need to select the best models and finally come up with the model that we want to use for forecasting into the future. So in this case, our error statistic is the root mean square error, RMSE, and it's quite a common metric that's used to evaluate model or forecast performance. And it represents the difference between the forecast and the test data that we saw before. So it's the standard deviation of residuals, the difference between forecast and actual, expressed in units of NDVI. We also use the Akaike information criterion, or we can use the BIC as well. And both those figures aim to optimize the trade-off between goodness of fit and model simplicity. So they try not to give you a really complex model that generates a low error. So they aim to be a fairly holistic measure of, I guess, how good your model is. There's a few different schools of thought on which one's better, although for predictive models, AIC is quite a common metric. So I think we have our data. So I apologize for the wait there, and thanks for your patience. We can now visualize the time series that shows the phonology that we talked about before. We've split our data, as I said, and then we will iterate through, as I said, that is quite quick. So 81, and then we need to run the different function that we defined above here for running those 81 models. So this one can take a little while as well, although it looks like it'll, at least we get a progress bar, so it feels like we're actually going somewhere. So you can see in this cell here, we've defined a function which is called OptimizeCerima based on the parameters list, which we've defined earlier. And then that function, OptimizeCerima, is returning ascending root mean square error data frame with parameters, the AIC and the RMSE. And it's iterating through the ranges of P, D, and Q that we selected. So this cell here, I realize there's quite a lot of code there, but it's just, I guess, defining that function. And in the cell below, we actually implement the function on our parameters list. So now it's 100% run on the 81 different combinations of parameters that we listed. And we can print the result table sorting on AIC and also on error. So because we sorted by error first, we get the lowest RMSE at the top, that's model 0, and the RMSE is 0.018 or thereabouts. The AIC, we often want to select the lowest AIC. So I guess looking through, the lowest one is 205, model 10, although the RMSE is a bit higher. For this particular notebook, users can really select any model for the next steps, especially out of those top 15 results. But we've just selected model 0 with the lowest RMSE for further forecasting. So this is where the user can select the model. In this case, we've selected model 0, and then we can store the parameters from the selected model and fit it to our training data. So again, we can see we got the same error and AIC. And before we go and do a back test or have a look at the back test and then use it for a final forecast, we'll have a look at some diagnostics. So the Cerima module in Python gives us quite a neat little function where we can plot all the different diagnostics, and there's a description in the notebook on what that actually means. So the standardized residuals in the top left, we want to see that that is consistent over time. So we don't really want to see any pattern in the standardized residuals, and that's a common theme for a lot of the different plots. We don't want to really see a pattern there. The histogram and the kernel density estimation, or the estimated density, is basically a probability density function fitted on the residual, so it's fitted on the error, and we want to see that the residuals or the errors are kind of normally distributed. So we don't want to see lots of errors that are positive or most of the errors that are negative or skewed. And then the QQ plot, we also want to see the residuals, I guess, following the red line generally. And for the parallelogram, that's looking at lags over time. So the x-axis is the lags, and anything that's outside the ribbon is statistically significant. So we don't normally want to see lags greater than 0 statistically significant. In this case, we do have 1 or 2 that are. And we've also noted here, a note in the notebook, is that the QQ plot and the parallelogram generated for this model actually show that there is some pattern in the residuals. So that means that there is remaining variation in the time series that we haven't accounted for in our model. And so the user might want to experiment with different parameter values. So it may be a greater range of P, D, and Q, which adds to the computation time, but it might improve the model. So we can actually see that there's a curvilinear pattern in some of the residuals here that tells us that our model perhaps has some variance that we haven't accounted for yet. But we've stuck with it anyway, so we're going to use it for the back test forecast. And this particular cell generates the figure that we saw in the slides earlier, where we've plotted the training data that we use to train the model, the test data against which the forecast is assessed. And then finally, we can actually use that model we selected to forecast into the future. So instead of running the model on the training data, we run it on NDVI using the same parameter values. And that should run fairly quickly. And then we can forecast the result, as we said, with a confidence interval as well. So that brings us to the end of the notebook. I'll just return very briefly to the slides in terms of what the next steps or what users might think about beyond this particular notebook. So as I suggested there could be an improved model. So our diagnostic plots show that there's certainly potential to improve the model, and I'd be interested if users could give us a more accurate forecast. That would be great to see. And we could also consider a spatial component to our forecast. So one example of that would be running our forecast on a time series of pixels rather than something that we have to calculate the mean of over X and Y, which was the cell that took a really long time. The trade-off with that is that it does become highly computational to do that over a large scale. So you do need some computational resources. But that concludes really all I had to say in terms of presenting the notebook. So just acknowledge our partners and everyone for coming along today. And thanks very much, and happy to take any questions or comments or hear your thoughts about the notebook.
Thank you very much, Michael. Actually, everybody's clapping for this amazing work. Any comments for Michael?